All right, well, I'm going to get started. I'm James. I'm in the statistics department. And this is sort of the premise of this talk is also the premise of the class that I teach, which is 208, which is statistical machine learning. And the idea behind this, and talking specifically about binary classification, is that in my experience, binary classification, if you focus on the main developments in machine learning, within that context, you can get a lot of the main ideas that are applied broadly for many different types of problems and many different settings. So just by looking at this and the motivations for different methodological developments in binary classification, we can sort of extrapolate these ideas out to the remainder of it. So it's sort of by studying this, you can possibly get to a point where you could pick up a machine learning paper and get what's going on, even though it's a completely different problem setting. And so I think that's a valuable skill to have, so that's the premise here, is that it's not that I think that binary classification, every problem can be stuffed into that box, but I do think that it's important to think about it and to think about what we've learned from it. And another thing is the story of machine learning, and I think more broadly data science, is that there are competing narratives going on, motivating different methodologies. And so the narrative I'm going to give right now is relatively non-statistical, whatever that means, right? So non-probabilistic is probably a more accurate description. So I'm not going to be talking very much about probability distributions. I'm going to be more talking about properties that these algorithms have, which I think is sort of more of a philosophical shift from the traditional statistical approach, which is modeling based, which is still valid, but there are other narratives out there, and I'd like to give an account for one of those at least here. So if you'd like to follow along, the easiest way to do that is just to go to my webpage and then scroll to the bottom of the index.html, and you can see a link to this part of my GitHub repository. I just threw it into the repo for my class, so it's sort of buried in my class repository, but the link should do it. So it's this jsharpnack.github.io. And you can either follow along on the lesson on NB Viewer here by clicking on this link, if it's still up, yes. And you can toggle off the code if you would like. I'm not going to focus on the code here. I'm going to focus more on the principles and the ideas. All right, so I'll get started. So I'm going to start with an application that does not at first glance look like necessarily like a classification problem, or that it's very easily thought of as an application or as a classification problem, but we're going to tackle it as if it just were a simple classification problem at the moment. So actually, I'm going to use my own notebook. Okay, so the idea is that we can extract a network from any social network like Facebook. So this data set that I'm going to be working with is this Facebook network that's available on the SNAP website, which is a Stanford network analysis project. And this is I'm just going to be working with 300, a little over 300 vertices in this network. So each of these correspond to users on Facebook, and then edges correspond to friendships. And it's of course of interest to Facebook and other social networks to be able to predict whether there's going to be a friendship in the future. So for this part, what I'm going to do is I'm just going to read in this friendship network, and then sometimes I'm going to hold out some of these edges. So I'm sort of simulating the process of forecasting a friendship, the process through which you would forecast friendships. So I'm going to hold out 10% of those edges, and then I'm just going to say, using the remaining edges, so this is going to be our training network, can I predict where there are edges that are going to be formed, right? So can I predict the edges that are in the test set? So this is the application. So given two individuals in this network, individual I and individual J, if I can come up with features for that pair of individuals that can help me predict whether or not they become friends, so whether or not they're friends in the test set, then that might become a valuable metric that I can use later on when I'm implementing a friendship recommendation system. Yeah, Robert.
When you mention features, you're only going to work with connectivity data, correct? There's no like underlying.
That's right. That's right. So so Facebook has access to much richer information, right? So I think part of the fun thing about this is that we're only going to be using network information and network information for the training set. So of course I just had, the data set is just a static network. So I had to think of it as if some of these edges were going to come after some of the other edges. So I just hold out 10% of them. And then treat it as if I have a static network of 90% of the edges, and then I'm using that to predict the other 10%. So this is the setting, is that I have my training network and test network, and the vertices are the same vertex set, right? So the ith individual in the training network is the same as the ith individual in the test network. That's an important feature of this problem. So here's a visualization of the training network. Here's a visualization of the test network. And of course, the test network being 10% of the edges is much more sparse. See that this is much more sparse. Okay. So the title that we listed, I said it was going to be overfitting and this idea of surrogate losses. I'm not going to go over overfitting. I realize that it's not as it's a little more well-known, overfitting, the idea of overfitting, and it's going to come up naturally in the next lecture, or in the next workshop. Sorry, not lecture, workshop. So instead, I'm going to spend some time talking about how you can evaluate a score, just a single feature that you can use in recommendation systems using these ROC and PR curves. So forgive me if some of this you already know. Hopefully the application is new to you, and then it can be at least sufficiently interesting. So there's a couple of faces that are in my 208 class, so some of this will certainly be redundant for them. Okay, and then also, you can always look at the Python code here on your own. You can always look at the Python code on your own, and then maybe you can see how I tend to implement these things using the packages that I use. Okay, so one natural thing that we can do, and this was a part of a methodology that was proposed early on in the link prediction literature, is we can just say, well, let's look at the neighborhood in the training set for two different vertices, right? So we have two different individuals. Who are they friends with, and do they have mutual friends? And so if I look at I think these are two of the vertices. I have their index sets for their neighbors here. Yeah. So vertex 1. This vertex, vertex I, is connected to the 279th individual, the 321st, 132nd, and so on. Right? And then the second one is connected to the 194th, the 327th, the 77th, and so on. Right? So I can just say how much overlap is there between those two. So when I take the union or the intersection of these two, I get just the 72nd vertex. And actually, it's pretty rare for any two pairs, any random pair of individuals. It's pretty rare for them to have a common neighbor. So one reasonable thing to ask is, well, when they do have a common neighbor, if I just say, well, they're more likely, if they do have a common neighbor, to form a friendship in the test network, then that might be an evaluation metric that I could use in a recommendation system for friendship networks. Okay, and I can generalize this, right? I could just say, well, the size of the number of mutual friends that they have is going to provide for me a score, and if that score is high, then I'm going to say that they're more likely. Then I'm going to recommend that friendship first between I and J, that they're more likely to have a friendship in the test set. Okay, so I can do this, and what I'm going to do is I'm just going to specify a threshold. I'm going to call this tau here. And so if the number of mutual friends that they have exceeds or is equal to this tau, then I'm going to say that they have a friendship, right? That's going to be my recommended. Then I'm going to recommend that they are friends, right? So that will be the predicted label is a 1. Is an example. So this is an example of a confusion matrix. So what happens is that when the predicted label is a 1, I can actually see what the true label is in the test set. I can see whether or not they were friends. If they are, then the true label in the test set, then the true label is 1. And if they're not friends in the test set, then it's a 0. And there are far more zeros than there are ones. The graph itself, before I split it into training and test, it was actually a pretty sparse graph to begin with. And then I extracted only 10% of those edges. It's an extremely sparse graph. So there's far fewer, for any pair of users, there's far fewer, well, there's a lot of zeros and not a lot of ones, where ones correspond to them actually having a friendship. And so what I can do is I can say, well, how many times did I predict that there was, for any given pair, how many times did I predict that there was an edge in the test network, and then maybe I got a true positive. So the true label is actually a 1. So this is the number of true positives for this specific choice of tau. The tau, remember, was this threshold. There's a threshold on the number of mutual friends that I and J had. And so one thing to notice is that actually, first of all, it's going to be very difficult to solve this problem because there's far more zeros than ones, right? So if I were just to, say, flip a coin and say, if the coin is heads, then let's predict it as a friend. And then if it's tails, let's predict it not as a friend. It's going to do very poorly in the sense that there are so many zeros, it's very hard to find the ones within those zeros. And we'll see this actually empirically in a little bit. That random guessing does extremely poorly in this setting where we have class imbalance like this. But I just really, with this, I want to introduce the idea of a confusion matrix. Is we can look at the different types of errors and also the number of times we got we made a friend recommendation correctly, and number of times we didn't make a friend recommendation, and it actually turned out not to be a friend in the test set. Okay. So the key thing is to look at the ratio between things in this column of the confusion matrix. Okay? So the ratio, when I predict it as a 0, there's far more zeros by several orders of magnitude than ones for the true label. When I predict it as a 1, the order of magnitude difference here is significantly smaller, right? It's a factor of 2 or 3. This is one thing that indicates that actually we're doing pretty well, even though we got a lot of errors. Okay. Now, if I increase that tau, I get a different confusion matrix, right? So now I say that 2 people are likely to be friends if the number of mutual friends that they have exceeds or is equal to 5. Now I have, now it's more difficult for me to predict a 1, really, right? I've reduced the total number of predicted 1s. So they're moving out of here. But if my score is doing anything at all, if a higher score means it's more likely that they're friends, then the proportion of true 1s versus true 0s when I predict it as a 1 is starting to shift. Some of these entries are coming out of these true 0s and coming into this true 1s. And that's what we see here in this. And when tau is equal to 10, there's far fewer predicted 1s, but this proportion is shifting down here in the confusion matrix. It's moving to more true 1s of the predicted 1s. Okay. So that's sort of the idea, is that typically when you have a score, you can vary this threshold and get a different confusion matrix every time. Now the question is, how can we evaluate the quality of our score that's in a way that's independent of this choice of threshold, right? I could look at all sorts of things if I had this confusion matrix. Right? I could take various combinations of these entries and ratios of these entries, and that's, we'll talk a little bit about what those are. But I also want to make sure that in the end, I can make my evaluation independent of tau in some sense, tau independent. Because really, if you think about what we're doing, is we're just providing a score, right? So if someone is recommended the top scoring pairs, right? The top scoring possible friendships, then they might flip through several of these friendship requests until they find one that's relevant to them, or they might just say, well, there's none that are relevant to me here. I'm going to scroll down on Facebook. So in those two scenarios, there's effectively going to be different taus are going to be relevant. They're going to move down into lower and lower scores as they move on. Okay. If there are any questions, feel free to interrupt me. But this stuff is pretty straightforward. So I'm going to jump over to some notes that I have. That should look familiar to some of you. Okay. So this is a prediction method, what we have here. We have a given score. Right? This is this SI. And if it's greater than tau, so now I'm having this strictly greater than tau, whether it was greater than or equal to. If it's greater than tau, then I'm going to say that it's equal to 1. Otherwise, it's equal to 0, this prediction. Right? And in the network example, this I is actually a pair of vertices. Right? So we've enumerated all the possible pairs of vertices, and then we're going to predict whether or not they're friends or not in the test set. Okay, so the confusion matrix looks like this. This is actually I've seen in the confusion matrix that we plotted above. This was a 0 and this was a 1. This is a 0 and this is a 1. So we have to worry a little bit about that. so just sort of transpose it in your mind when you're looking at it on the notebook. Anyway, so of course if we predict it as a 1 and it's actually a 1, we're going to call that a true positive. If we predict it as a 0, it's actually a 0, we're going to call that a true negative. So the positive and negative there correspond to the prediction in this label, and the true and false correspond to whether it was an error or not. So the two types of errors are false negatives and false positives. So in statistics, for statistical testing purposes, we call this a type 1 and a type 2 error. Yeah. So the basic prediction method that I outlined here is, first of all, we calculate a score, right? That was the hard part of the method that I just outlined, right? So that was, first of all, it's something that we typically will have to engineer, or we'll have to learn in some way, and that's what will lead us to classification. But in this example for the networks, this score, it was the number of common neighbors. So then what we do is we order these scores, right? Because this is exactly what happens in a recommendation system. We start with the highest scoring pair of nodes, make a recommendation for the friendships, and then we move down. So the idea is that we're going to select a permutation of these scores. So notationally, this is more complicated than conceptually. So the idea is that a 1 is the highest scoring individual, or highest scoring pair. A 2 is the next highest scoring pair, and so on. So we've ordered these scores. And now what we're going to do is we're just going to say that the top T, capital T, are 1s, and the remainder are 0s. So this is equivalent to selecting a threshold, right? Because I could have selected whatever threshold will give me that the top T are the scores that are above that threshold. So I'm just going to think about, how does the confusion matrix change as I change this capital T? The number, yeah. Okay. So let's look at this example here. If we have our scores, say and this is for an arbitrary score. So in this example, just think of the score as being any real number. So I have this list. So I've computed the scores for my classifier, and then I've ordered them in descending order. It starts with 3.1, then it's 3, then 2.8, 2.6, and so on. Then I selected capital T equal to 6. Right? So I said the first 6 entries, the first 6 records are going to be 1s, and the remainder is 0s. Right? And then I can look at what their actual Y's are, what their actual values are for the response variable. And then I can just say, are they 1 or 0? So in this made up example, we have a 1, a 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0. So these first 2 zeros that we see for the Y's, those are errors, right? Because this first 6 we predicted as 1s. So these were errors, right? And these in particular are false positives, right? We predicted those as positive, they were actually 0s. So that's one type of error. Then the remainder of them, we have some 1s, and those are false negatives, right? Okay. So we can get this confusion matrix for the specific T, and that's this 4, 2, 2, 4 matrix. Okay. Yeah.
Can you remind me how we calculated this?
So this is just any arbitrary score, right? So right now we're thinking about engineering a score, just proposing any score, right? So the point of classification is to find a score that does well in some sense, right? So this is all leading up to classification. But I think it's so a little, just to back up a little bit, why I'm talking about this. I think it's sort of important to think about how chronologically classification ideas have developed in practice, right? Because this is really how it happened, is with link prediction in particular, people just proposed certain scores, right? And then they could evaluate it, see how well they did in practice. And then they started thinking, well, how can we combine these scores? And so that's what we're going to do. And that's actually how sort of historically classification was developed as a field. So that's hopefully this talk sort of mirrors that. So if part of this is boring, you can just tune in whenever it becomes interesting, and hopefully you'll tune in eventually.
Yeah. Question. So those scores, are they equivalent of rankings, or do they have like some other inherent information in that?
So typically they're extracted from some external information, right? So for the testing network, we extracted them from the training network using it. And so if I propose a score, it's equivalent to a ranking, right? Because I can order it and do this, right? So so usually the way people think about these things is that the score is a proxy for the ranking, right? If that makes sense. Okay, cool, yeah. So, sweet. All right, so the receiver operating characteristic, or the ROC curve, is it's really just based off of two numbers that we can extract from this confusion matrix, right? So the confusion matrix is 4 numbers, right? It's very difficult to deal with 4 numbers, right? It's hard to plot it, it's hard to visualize it. So we typically will extract 2 numbers out of it, and then we'll see how it varies as we vary t, capital T. So the ROC curve, it's based on this true positive rate, which is also known as recall, and then the false positive rate. So the true positive rate, we just take our characteristic, or our confusion matrix, and we look at the number of true positives and divide it by the total number of actual positives. So the total number of true ones. And then the false positive rate, we take the number of false positives divided by the total number of true zeros. So the true positive rate in that example that we had above, here I'll zoom out a little bit so that we can see them both at the same time. Yeah. Okay, so the true positive rate in this example that we had above, you know, the number of actual positives is always 6, right, in that example. And the number, actually, there might be, this is a mistake that I had before. 1, 2, 3, 1, 2, 3, 4, 5, 6. Yeah, no, this is right. So the total number of positives is actually 6. The total number of negatives is actually 6. Right? So that's going to always be in the denominator there. It's just one number as we vary t. The things, yeah, sure. Yeah. So t is so. Let's think about it more intuitively. So in a recommendation system, say I'm recommending books to you. Say I'm Amazon or something like that, and I'm recommending books to you, and I have some idea of what you like, and so I turn that into a score that says, you know, each book in the whole library has a score. So we start with the highest scores and recommend those to you first, right? And maybe you're really bored and you're just scrolling through it because you have nothing better to do with your life, right? So then T is going to be very large in that instance, right? Because you're going to spend a lot of time looking at many different books. And so at some point, at some point you're going to stop, and then those are all, we can think of those as predicted zeros, right? So typically T is either selected adaptively in that sort of a way, or it's thought of as like a tuning parameter, right? Depending on the application. Right. So yeah, T in words is the point at which we stop saying that they're ones, right? And start saying that they're zeros, right? When we make this ranking. Does that make sense?
So it's not the number of, like, when you're looking at the different vertices, it's not like you're saying I'm looking at a sample size of 6 or.
Yeah, so going back to the example in the network prediction, you know, the link prediction application, that's the number of edges that we're going to recommend. And so, yeah, there's details that might be relevant to the link prediction application, right? Like Facebook might be making different recommendations to different individuals, but we're just going to think of it as we have a certain budget of friendships that we can recommend, right? And that budget is T, capital T. And then we see whether those T that we do recommend are ones or zeros. Yeah, so cool. Thanks. Yeah, so a lot of this stuff, and the point of talking about this is that you know, the metrics that you use, the way you think about the metrics are all domain specific, right? And so recommender systems, data sets with large class imbalance, they're very different than other classification settings. So it's good to think broadly about how do we evaluate scores, I think, for that reason. Okay. So the true positive rate, really we're just looking at the number of true positives versus false positives as we vary T. Right? So if T is very small, right, then we just say T is just 1. Right? So we're just saying the top scoring one is a 1, everything else is a 0. Right? So this is relevant when we're recommending a single book to a user, right, to an individual, and they either buy it or they don't, right? Or they maybe view it or they don't. All right, so when T is equal to 1, then our true positive, this first Y in this ordering is a 1. So we get it correct, right? That top one was correct, they bought the book. So the true positive was a 1, but the actual positives was a 6. So this is 1/6, even though we had a very good true positive rate. This true positive rate, or sorry, even though we predicted that one exactly correctly, the true positive rate is 1/6. And then as we increase T, we're going to get a couple of errors, and those are situations where this doesn't increase. Right? This true positive rate doesn't increase. So say T is 2 now. So we predicted the top 2 as 1s, and then we got one book was bought, 1 book was not bought. And so the number of true positives stays 1, and the true positive rate is 1/6 again. And then so on. The false positive rate is this number of false positives, right? So it's so it starts off 0/6, then it goes to 1/6 because we had an incorrect one. We predicted something as positive, and actually it was negative, and so on. So then if we just plot these two against each other, we get our ROC curve. So we say, sorry about this, so the true positive rate against the false positive rate, when we plot that, that's this ROC. So this is just a silly vignette. Typically what you see is a curve that's going to be a bit above this straight line of slope 1. And it's better if it's over in this top corner, this top left-hand corner. Yeah, and this is my drawing of what we actually get here. Forgive me for bad drawing. But yeah, so this line is what we expect to see from random guessing, and we'll see this demonstrated above. Okay. So what the point of this is, if we want to compare two different scores, we can look at their ROCs, their ROC curve, and then we can see maybe some are better at certain false positive rates than the other score, or maybe one score just always is better than the other score. Okay. So yeah, sure.
So this is a possibility, right? So you get a true positive rate versus false positive rate graph being below this.
Yeah, it is possible. So part of it is all of this is random, right? Data is random, so all of this is sort of random, your score can be very bad, right? Like if I were to just invert my score, if I were to say, let's take this S and let's just make it negative, right? Then everything is flipped here. And now when I start predicting ones, I'm going to get a lot of errors, right? Because when you look at the true labels, we're now going from right to left. So that would be an example where it would actually dip below. It's because my score is doing worse than random.
So the way to interpret that would be that if something falls behind this, it's a bad score, and if something falls above it, it's a good score.
So it's better than random, which is sometimes that's a low bar. Sometimes that's actually a pretty good thing to have. Right? Sometimes random is very difficult.
When you say it's better than random, you mean to say that this line basically says you have half chances of getting it right.
Yeah.
Like
So.
Random chance.
So the way you should think about it, if I just randomly generate a score, right, according to a uniform 0-1 distribution, right? So I just draw a random number between 0 and 1, then this is what we should expect to get from that score. There should be no real information coming out of that score, right? If anything makes sense in the world, that's something that should happen. So yeah, so this is sort of like a very weak benchmark. In some applications, maybe that's actually a pretty reasonable thing to try to shoot for, rather than random guessing. But yeah, so using this ROC curve, we can compare two different scoring mechanisms. Yeah.
The slope of the line depends on the true size of the proportion of the splitting. Is that right?
The true size of it.
So like consider the Facebook example that you had earlier, where you were very sparse.
Yeah. So in the here we go. Let's just look at this. So here's the ROC curve that I get from this. And actually, even though we have high class imbalance, this is actually just a random guessing, and the slope state is still 1. So, but the PR curve, the story is different. So anyway, so I'm jumping to the notebook here, and I'm just going to look at the ROC curve for the common neighbor score versus random guessing. And it actually does significantly better than random guessing. And that's partly what's happening is that because of the large class imbalance, all of our data points on here have extremely low false positive rate, because there are just so many zeros. And so that denominator in the false positive rate is extremely large. So this false positive rate is very small. Are there other questions? This is sort of a lot of concepts are sort of compounding on each other, so it's easy to get lost. Sure. Yeah, so if you had a certain true positive rate and false positive rate in mind, then you could set that t. Sometimes your application will just beg for a certain t, right? Like maybe you have so much space on your web page to put recommendations, and so your t is just the number of items you can put up. But it really depends on how you're evaluating the cost of different types of errors. Right? So it's good to have different ways to evaluate. So true positive rate and false positive rate is one. Precision and recall is another, which I'll talk about in a minute. Yeah. Okay. Is this going down? Okay, so this example is the example that we have that I'm mentioning. So in recommendation systems, typically what's going to happen is it's very typical that there are a lot of zeros and very few ones, right? You don't buy, 10% of the books in the world. You buy just a couple of them. So this happens, of course, in link prediction. So in this sort of application in search engines, this happens. You don't want to. You're not going to click on 10% of the web pages. You're going to click on 5 of the web pages in your Google search. So most of these examples in recommendation systems, there's an extremely small number of ones. Well, part of the issue with the ROC curve, and just looking at the false positive rate, and we just saw this, is that this number is huge, right? This denominator is huge. So this false positive rate in those examples is always tiny. Right? So this makes the curve almost trivial, right? It pulls all of the data points in the ROC curve to one side. Right? So in these applications, we typically will look at the precision instead of the false positive rate. So the recall was still this true positive rate, so that's still relevant. And the number of true negatives, so those zeros we predicted as 0, doesn't enter into the true positive rate. Right? And that number was huge. Remember that was like 10,000. Right? So we don't want that to really enter into our metric if we have this massive class imbalance. Right? Because not recommending a web page and it being a web page that wasn't very relevant is an extremely low bar. Right? That measuring our error in that way is an extremely low bar for recommender systems. So instead of the false positive rate, we look at the precision. The precision is this true positive rate over the predicted positives. And so instead of all of the positives, the true positives, we look at the predicted positives. And this jives with kind of how we were looking at it, right? We were thinking of it before. So I'm going to jump back up. Pardon my jumping. Before, I said, well, let's make t equal to 3, for example. So t is very small in that example, and this is sort of realistic for a lot of recommendation systems. It's a very small t. I got 2/3 of those predicted positives correct. Right? So the precision, and that's what the precision is, the proportion of predicteds that you get correct, was actually pretty good, right? 2/3 is very good in that example, right? So that's what the precision reflects. It's the proportion of true positives over the proportion, or it's a number of true positives over the total number of predicted positives. So I can do that, and the precision starts at 1 in this example, right? The very first one, the top scoring individual, was actually correct. So it starts at 1, then it goes to 1/2, but then it jumps back up to 2/3. But typically what happens is the precision is quite large for low recalls. The recall is this true positive rate, and then it drops down, right? And it levels off. And where it asymptotes in this is sort of dependent on that class imbalance. Okay. So we typically will plot the precision against the recall, precision on the y-axis. So if we look at our example here, so first of all, let's just think about random guessing. In random guessing, I have a random score. I'm just generating a score uniformly at random. Right? So I'm just ranking them arbitrarily. The recall, I can change the recall just by changing the t, right? The capital T, the number that I recommend. So that's fine. That can go from. But the precision stays extremely low, right? And that's because the proportion of true ones out of the full data set is extremely low, and that's what this value is going to be roughly. Is the proportion of true ones in the data set, right? So random guessing, if you look at the PR curve, is very bad in this case, right? And this is reflected in the class imbalance, right? If I choose a possible friendship at random, because there's so few friendships in this network, there's so few edges in this network, I'm going to do quite poorly, right? It's very unlikely to get that friendship. So this is reflected in the PR curve. Now, with the common neighbors, the precision starts around, between 0.6 and 0.8. If you actually look at the t's for which this is, for which you achieve this, it's very low. So there's a lot of variability for these low t's because the precision is dividing by a relatively small number. And then as we increase t, it'll drop down. But even at this level, say our precision is somewhere around 0.5, that means that half of the ones that we're predicting are actually true ones. That's very good for this data set, right? If half of the people that I recommend to you are actually friends, that's actually a really good benchmark. So anyway, so the way we evaluate scores is going to be very application dependent. So I think I'm moving more slowly than I anticipated, but that's probably a good thing. So so we might not, I'm not sure where we'll get, but we have another session and I can sort of adapt things to depending on how it's going. So are there questions about the evaluation? Yeah. Okay. Yeah, sure.
So in the earlier graph, I did not get there is a notion of T.
Yeah, so T is sort of suppressed, right? Each T gives me a different point on the curve, right? But you don't actually see it. It results in either a true positive rate or a false positive rate, right? So part of the issue when we're looking at ROC curves for class imbalance, all of these data points have very low false positive rates. So each of these data points corresponds to a different T, different selection of T. We could have plotted, say, true positive rate against T, for example. Or we could have plotted, and that's another thing we can do, or precision, maybe more importantly, precision against T. But this is a bit more common. It serves roughly as a proxy for that.
But using this, you're trying to say that I want to use both precision and recall to have.
Oh, for selection of T. Yeah, so there's heuristics, and again, this is sort of more of an application-dependent choice, right? So really, you want to think about, how am I losing money, or how am I impacting customer satisfaction, or something like that, to choose exactly how you select T. For example, one thing that's common is a geometric average of the precision and recall. That's called the F1 score, and it gives us a single score for every T, and then we just say what's the best of those. So there are ways to do this, but again, that's just a heuristic, and it'll depend on your application whether that's the right one or not. So typically, what you find is certain domain sciences have different benchmarks. And it's because people who know more about that domain than I do have really thought about what's important to us. Right? And that's sort of how this works in general. But it's good to have sort of a lot of different ways of evaluating scores on hand. Okay. Okay, so I'm going to, let's think about, so first of all, one way to interpret the number of common neighbors is the number of ways that you can go from person I to person J with just 2 hops in the network, right? Because you go through a single point from I to J, right? And that single point is a common neighbor to I and J. So another interpretation of this number of common neighbors is the number of paths that are of length 2. You just hop twice in the network, and you get from I to J. So the number of unique paths that do this. Well, we can generalize this, right? We can allow the length of these paths to increase. We can say how many different ways can I hop 3 times and get from I to J. So in this example, I created one feature for this number of hops going from 2 to 7. I think, yeah. So there are 6 different features. And we can plot one against the other, right? So we can say for every IJ pair, for every 2 individuals, I can just say, what's the number of 2 hop paths? So that's the same as the number of common neighbors. And what's the number of distinct 5 hop paths? So the number of distinct paths that are of length 5 that go from I to J. I can plot these against each other. So now instead of a single score, I have two different possible scores. And I can say, well, let's look at just the positives, which are these red dots, and the negatives, which are these blue dots. Right? There's far more negatives than positives. And so this is, so now the challenge is instead of a single score, I have two possible scores, and actually I have 6 possible scores, and I can actually combine them in any way that I like. Any combination of those into a single number is a valid score. It's a valid possible score, and now the question is, how do I select those? So actually, this is one interpretation of what classification methods do. So so a lot of you have probably heard of logistic regression. We're just going to think of it as a black box for producing a weighted combination of these features. And then I'll talk a little more in detail about what that means, weighted combinations and things like that in a minute. But for now, just bear with me. Logistic regression, you can think of it as finding a line. So now I'm just going to think about these 2 dimensions. Finding a line such that if it's on one side of this line, if a point is on one side of this line, then we predict it as a 1. If it's a point on the other side of this line, we predict it as a 0. Okay. And so now we can just say, well, how often are we right and wrong, and in what ways, right? We can think about our true positive rate, our false positive rate, and so on. Subject to this. Okay. So we can create a confusion matrix for this line, right? We can do this, and that's fine. And the hope is that by combining these multiple features, we can get a better confusion matrix in the sense that there's higher numbers on these diagonals, right? Higher true negatives and higher true positives. That's the hope. That by combining features, we can do this. Okay. So I could say, look at these metrics, for example, for logistic regression. So this is the PR curve. Sorry, I didn't label it. Versus the single scoring. Actually, it's not doing significantly better. This is just for the 2 features. Yeah, sure. Yeah, sorry, I labeled it in everything other than this. I got this. Yeah, sorry. The blue curve is the common neighbors. It's just a single score. The red curve is the combination. I just missed this one when I went back through my notebook. Sorry about that. Okay, so that's so that leads me to hyperplane methods. Okay, so logistic regression, right now we're just thinking of it as a black box that produces this line. Right, this line is what we want because if it's on one side, then we say it's a 1. On the other side, we say it's a 0. Right. Okay. And so say we have a data set. So this is just a vignette. It's a simulated data set. It's not a real data set. And the positives are the red ones, the negatives are the blue ones. And we just have these 2 variables. Right? So now the question is, how do we determine what a good hyperplane is? Right? What a good line is? So I'm calling lines in higher dimensions are hyperplanes. Right, because they can separate your space into one or the other component. Okay, so what's this optimal line? And for example, this might be better, a better line here. Okay, yeah. So how can we evaluate that? Right. So let's just think about a very simple way of evaluating a line. And we could just evaluate the performance of a given line just by the number of errors that we get. Right? So this plot is, I've just sub-selected for this given line I've just sub-selected the points that are on the wrong side of the line. Right? So before I said it was reasonable to say that on this side we have reds, we're predicting a red, on this side we're predicting blue, and I just sub-selected the points where that was incorrect. Okay. So one thing I can do is I can just say, well, how large is the set of misclassified points relative to the size of the number of points in total that we have. So that's one way that I can evaluate one of these lines. So I'm going to skip over. Okay. Okay. So first of all, it's important to think about what a line is. So first of all, an equation, so a line, the equation for a line is we just say, well, it's an equation of the form that beta 0 plus, now we have a weighted combination of the x's. This is a hyperplane when p is greater than 2. It's that beta 0 plus this weighted combination of the x's is equal to 0. That's the equation for a line. And then if we want to say, or hyperplane, if we want to say if it's on one side or the other, then we just say, well, is it greater than or equal to 0 or less than or equal to 0? That's one way we can do this. Now this beta corresponds to the normal vector for the plane. Right? So the normal vector is the vector that is orthogonal to every element in the plane, every vector in the plane. So you might remember from your undergrad days thinking about this idea of a normal vector. So that's the correspondence, this normal vector to the plane, and that's the correspondence to the beta coefficients and this picture that I had of the line. So now we can think about finding a line as the same as finding this beta vector, this list of numbers from 0 to p. And this beta 0, we call this the intercept. Okay. So that's the idea behind these separating hyperplanes. And broadly, for reasons that we'll see in a little bit, these are called margin methods, margin-based methods. Yeah. Okay. So the framework that I'm going to work within is called empirical risk minimization. So empirical risk minimization, the idea is that we have some notion of loss. And so if I propose one of these lines, before I said there were some predicted zeros, some predicted ones, and we just said, well, what's the proportion of misclassified points? My notion of loss there is just whether there's a misclassification or not. Right? So empirical risk minimization is a more general framework. It says, well, for any loss, we can just say, well, what's the proportion, what's the average of those losses? So to stuff this into, sorry, I'm going to have to jump down. Didn't think about how this works. Okay, so to stuff this into the 0-1 loss idea, we're going to say that the loss is 1 if this score is negative. So here, sorry. Let's just say it's 1 if we're misclassified, it's 0 if we're not. That's what the 0-1 loss says. Now, how does this relate back to the hyperplane? So one thing is that we can just say, well, let's define a score to be this beta 0 plus this weighted combination of the xi's, the x1 to x2. So if it's negative, then we're predicting it as a 0, right? Because then it's on one side of the line of the hyperplane, on the 0 side of the hyperplane. If it's positive, then we're predicting it as a 1. Now I'm just going to focus on the ones, the true ones, right? In this data set, because I can always just switch the role of the ones and zeros and then make this score negative, and then these losses stay the same. So I'm going to focus just on the ones and think about the loss, how to measure loss for the true ones. Okay. So the 0-1 loss, I can think of it as a function of beta, right? I choose beta, it changes the score, it changes the 0, 1 loss. It's either maybe some zeros become ones, maybe some ones become zeros in this loss. The issue is that this is a very non-smooth function of beta. What happens is that as you change beta, as you change this line, so looking back at this picture, as you change this line, some of these points might leave, other points, other misclassified points might enter in, right? And that'll give these discrete jumps in this average misclassification rate, right? This misclassification rate. So if we were trying to optimize beta based on this, then it becomes very difficult because of this discontinuity issue, and so on. So it's very difficult to turn it into an optimization problem. It's not always impossible, actually, in certain contexts, but for this context, working with the 0, 1 losses is very difficult. I don't know. Yeah.
Can you please tell once again what do you mean by hard or like smoothness in this?
Yeah, so I think it'll become a bit more clear when I start plotting the losses. So we'll see it in a second. I think if it's not answered in 5 minutes, then bug me again, please. Thanks. Okay. Sorry, this is a bit more of a mess than I realized. Okay. So one thing that we're going to do then is instead of the 0, 1 loss, we're going to replace it with other losses. So in logistic regression, we can rewrite logistic regression in this, what we call this empirical risk minimization framework here. So we have this minimize 1 over n, the sum of the losses. So logistic regression is a maximum likelihood method. It says, let's replace this loss with negative log likelihood. So I don't want to go too much into the probability because that's not the narrative that we're going through here. Instead, I'm just going to say logistic regression. It turns out that logistic regression, the loss is this log of 1 plus e to the minus si. That's what it turns out to be, logistic regression. So we're going to find the beta that minimizes this sum of losses, and we also have to include the losses when yi is equal to 0. So this is just yi equal to 1. So if we, but of course we can do that just by switching the role of 0 and 1, and then switching this s to be the negative version of s. Okay. So if we look up here at this plot, this is what the logistic loss is when here's yi equal to 1, and it's this decreasing function as s, and this is a function in the score itself. And then when yi is equal to 0, this loss becomes this increasing function. It's sort of mirror image of the other loss. Okay. So yeah. So the loss is different for yi being a 1 and the yi being a 0, depending on this score. Right? It'll look like one of these. Okay. Now there's another loss that's very common, and it's called the hinge loss, and it's one way to motivate support vector machines. So this loss is 1 minus si when si is less than 1 and 0 otherwise. And we'll see a plot of this, but this is also for yi equal to 1. So let's jump over. So I'm here, and okay. Okay, so I've plotted these functions. So again, this is the loss if y is equal to 1. So if we're trying to predict a true 1, then this is what the loss evaluates to, and this is as a function of the score, the SI, which remember is this weighted combination of the x's, right, of the features. So the 0, 1 loss, if s is negative, if the score is negative, and if the yi is equal to 1, then this is a misclassification. So the loss is 1. Otherwise, if s is positive on this side, then we classified it correctly, right? Because yi is equal to 1. So it becomes 0. So here is this discontinuity in this loss. And because when we look at the misclassification rate, it's just the average of these, right? And so that'll also be discontinuous. Does that make sense? And you would also have to include the zeros, which is sort of the mirror image of this. Yeah. So typically the way that these optimization methods work is you make little incremental steps for the data, right? And usually it's sort of you move in the direction of the gradient of the loss. But if you move if you make an incremental step for the 0, 1 loss for this misclassification rate, sometimes that won't change at all. Sometimes it'll suddenly jump to something completely different. And if you wanted to evaluate a gradient, for example, then that doesn't exist because it's a discontinuous function, or it's 0, right? It's 0 or it doesn't exist. So that's a little bit of the details of the optimization methods that one would shoot for. But if we look at the logistic loss, it's this red line, and I moved it up by a little bit. It actually hits around here, but I just moved it up a little bit. It doesn't really matter if we want to minimize a loss plus some number. That's the same as just minimizing that loss. So so it diverges as the score goes to minus infinity, but critically it gets quite small as the score gets very large. Whereas, yeah, sure.
So values on the right of 0 are values that we predicted
Yeah.
in 1,
Yeah.
and that actually are 1.
Yes, that's right. That's
And
right.
we're still penalizing for this.
So this is okay. Yeah. So let's talk about it. So first of all, because the logistic is it's shifted down a little bit, this actually asymptotes at 0. But there is a penalty for SIs that are above 0, right? Even though we correctly did this. So first of all, I'll finish talking about these individual losses and their properties, and then I'll address that issue. So the hinge loss, which was that 1 minus SI, if SI is below 1, and it's 0 otherwise, it's linear. It hits here, the 1, 0 point, and then it's 0. So it passes through the 0, 1 point, but it's not smooth here. Okay? At this point, there's this jump in the derivative. It has a discontinuous derivative at that point. That's one property of it, as opposed to logistic, which is smooth everywhere. But it's what's known as a convex function. So it's continuous, which is nice, and it's convex, which means that if you were to draw any line from one point, line from one point to another, then it would lie above this. So for optimization purposes, it's very nice to have convex functions. So this is just something to know. All right, we won't go into the details of optimization here. But it's very nice to have convex functions. And so we get that from this hinge loss, and we also get the continuity from it. But it's non-differentiable, or it has discontinuous derivative at certain points, which is going to cause issues. But it turns out, because of convexity, we can use something called a subgradient instead of a gradient for optimization purposes. Whereas logistic, if you know anything about it, they very much exploit this smoothness in optimization. Now, we could also just talk about square error, right? We could just do logistic regression on the yi's. The yi's are 0s and 1s. We have x's. Why not do logistic regression? Right? Of course, the model that motivates I didn't sleep enough last night. So the square error loss, it corresponds to linear regression. I've been saying logistic regression. Yeah, so we could for the square error loss, if we use the square error loss, that would just correspond to linear regression, right? we would be minimizing the sum of squares for this linear model. We could do that. Of course, we wouldn't believe the model of Gaussian residuals and so on that motivates linear regression, but it's something we could do. It's an algorithm, right? And you know, you don't have to believe a model to use it. The issue with linear regression and square error loss is that, you know, we have these correct predictions, right? Everything on this side is correct. Right? We predicted it as a 1 and it actually was a 1. Right? But the nice thing about logistic loss and hinge loss is that these are relatively small losses, right, for this correct prediction. Whereas with the square error loss, as we increase s, as s gets very large, this actually diverges. Right? So these are things that if we were to use a recommendation system, if we were to use this S in a recommender system, these are the first things to come up in our recommender system, right? They're the highest scoring points. But we're measuring loss as if we did terribly, right? So this is something that happens with square error loss. And this is really why we, you know, according to this sort of narrative of, you know, what is the behavior of these losses, this is why we don't use square error loss for classification. Yeah, and if you kind of look at the logistic loss and the hinge loss, they're actually not that much different. They have very similar behaviors, except for this discontinuous derivative of the hinge loss. But let's kind of try to visualize what these losses are doing. Okay, so I've proposed a hyperplane. That's this line here. And now I've just changed the size of these points according to the size of their losses. And so the blue ones are the blue ones are blue. On this side, I'm predicting red. On this side, I'm predicting blue. So actually, blues were the zeros, the red were the ones. Yeah, so we have positives and negatives. Yeah. So on this side, I'm predicting red. And so these blues are large. So this is for logistic loss. It's one thing. Didn't label this. Okay, so this is our logistic loss. This is what we get out of logistic loss. So, so let's focus on the blues. When we're over here, actually no, let's focus on the reds because that'll correspond to what we have up there. The reds are the yi's are equal to 1. Right? So if we are negative, so this is SI is negative because the normal vector is in this direction. So the SI is negative, is down here. And so we have these large losses for logistics. So if we go back up and look at the logistic loss, right, we're in this region. The SI is negative, our loss is quite large. Now, as we cross the hyperplane, so the hyperplane is 0 here, is this 0 point. That's on the line. As we cross it, it doesn't suddenly become 0 like it did with the misclassification rate. Right? So the misclassification rate, you didn't see any, when we looked at the loss-weighted version for the misclassification rate, you didn't see any blues on this side or reds on this side. Right? So we're going from here, negative S, we hit 0, we're on this line. Right? Now, as we increase, our loss decreases, right, in a smooth way. Right? And for extremely large S's, so if the point is sort of in the same direction as the normal vector, then it'll approach 0. But yeah, so we do get this property that we are penalizing points that are correctly classified. But if you squint at this curve, if you're going to require something like convexity, and you're going to require continuity, then it's going to be extremely hard to achieve that, right? Because think about the hinge loss. Say we're going to move around this point, right, for the hinge loss. Now, that's what our sort of degree of freedom. We're going to also require that it passes through this point. Then this line, the slope is going to become larger, right, until it'll just shoot up vertically. Right? And at which point, in the limit, it's no longer going to be a continuous function. And so that's the idea, is that if we want something that's continuous and convex, the best really we can do is this hinge loss. Right? But then it has this property that it's still, the loss is non-zero for correctly classified points. Yeah.
This property might actually be desirable. Like if you want to compare two separating hyperplanes,
Yeah.
give you the same classification results,
Mm-hmm.
but one sits more squarely in the middle of the two regions you're trying to separate.
Yeah. So the max margin methods do this. They, if you have, so with the misclassification rate, like you say, there were a lot of hyperplanes that could give you exactly the same classification rate. You can just perturb it slightly and nothing will change. And so how do you select which hyperplane to use? You use this sort of, you maximize this notion of margin. But that's something that I won't get to here, because to achieve that, it's a long lecture to go through the whole narrative of the separating hyperplane with maximum margin. So it takes a long time, which I'd rather just explain it through loss functions like this. Okay. So this is the logistic loss weighted points. So another thing, so this is the hinge loss weighted points. So if we look at it, the striking thing about it is a lot of the points just disappeared. Right? A lot of these points completely disappeared, and it's because with that hinge loss, it zeroed out those that we correctly classified where the score was greater than 1. It zeroes them out exactly. So we won't get. So there are these small points, and then all of a sudden it's 0. As we move up. So that actually might be desirable for a couple of reasons. Algorithmically, when we're working with, when we're using iterative algorithms, it might be nice to have sparsity in the data points that have non-zero loss. Right? You might only need to store those data points, and this is the idea behind support vector machines, is that we call these points at which the loss is non-zero the support vectors of the problem. So that's one property that can be quite nice about this. But other than that, statistically, the logistic loss and the hinge loss don't have that much different, usually don't have significantly different properties. There can be stability issues and algorithmic issues, but most of the time, SVMs and logistic regression in practice doesn't produce that significantly different results. It's because they both have these desirable properties that the loss at least limits to 0 as we get better and better correctly classified points, and so on. So usually it's practical reasons or algorithmic reasons why people choose SVMs versus logistic regression. So you might hear people say something like SVMs allow for kernels, but the same thing can actually be done with logistic regression. So, and we'll talk about kernels in the next talk. Okay. Now, if we look at square error loss, this is what we get. It's kind of a mess, but the idea is that these are correctly classified points. These blues that are on the blue side of the line, they're correctly classified points. But they're on the wrong side of the 1. Right? Same with these reds; these are correctly classified. Here is where that loss is 0. But remember, it has this; it's quadratic, and so it diverges on this side and this side of that line for the red. And so this is why we don't like square error loss for this problem. Okay. Now one thing is that if you've worked with logistic regression in practice or support vector machine, you know that you can add class weights to the losses, and you can say, well, let's penalize more heavily misclassified zeros versus misclassified ones. And if we think about 0-1 loss, there's a lot of reasons why we would want to do that, right? It might be that the cost misclassifying to 0 versus misclassifying to 1 is very different, right? There's very different costs associated with this. And so these are the two. So we were always looking at the y equals 1 losses, the losses for when the true label is equal to 1. So here's our 0, 1 loss for y equals 1 is this purple line. The black line is the 0, 1 loss for y equals 0, or I'm sorry, these are swapped. Okay. Anyway, so this is the y equals 1 loss, and this is the y equals 0 loss. The black is the y equals 0 loss. So we could more heavily weight the y equals 0 loss. So instead of a loss of 1 for the y equals 0, it's a loss of 4, for example. So now we weight, the ratio of the weights is 4 to 1. And we can just, because we have this idea that we're using the logistic loss as a surrogate, it's very natural just to multiply the logistic loss by that same factor when we want to do the weighting. Right? And we could also do that with the hinge loss as well. So this might be something that's relevant if we care more about a certain type of error, which happens quite a bit when we have class imbalance, like the original problem that we started with today. And so when we do these weighting, this is for example what we get for the logistic regression problem that we had before. If we're going to weight more heavily the zeros, for example, in this, there were equal number of 1s and 0s, so there's no real reason why you would do this unless you actually, for some reason in your application, misclassifying zeros was more costly. So maybe it's not very expensive to send out flyers to individuals, and each flyer could produce a bit of business, right? So you want to err on the side of sending out more and more flyers, right? So the zeros are actually, missed business is more costly in that sense. So that's just kind of a random ad hoc example. So this is our after we do a weighting, and what I do is I make the weighting so that the relative. So this is for the Facebook network example, and I make it so that the relative weights are proportional to the class imbalance in the problem. So the proportion of 1s versus 0s in the all possible pairs was the proportion of the weights for the losses, right, is equivalent to the proportion. And this is sort of just a default thing in scikit-learn. So it's very natural just to do this and say, well, scikit-learn, when you run your logistic regression, weighted according to the true proportion of 1s versus 0s. And what we end up getting is that our new precision recall curve is significantly better for this newly weighted logistic regression, as opposed to this was our old score. And remember when we used logistic regression before without the weighting, it didn't do significantly better than this old score. So the point is that, you know, we've motivated this idea of surrogate losses as ways of finding weight vectors, right? Ways of finding coefficient vectors when you want to combine features to form a single score. But then, by thinking about the fact that it's a surrogate loss for 0, 1, we can introduce this idea of class imbalance very naturally. And then it actually produces significantly better results in recommendation systems. Let's see what else. So I also applied this to support vector machines and compared the two. So SVM. So the difference between these two might just be randomness in the samples themselves, because the low recall region might just correspond to a difference of a couple of misclassified points. So I'm not going to read too much into the difference between these two. They're both performing significantly better than significantly better than the unweighted versions. So, okay, are there questions? Pretty much done.
So how would the loss function look like in self-rated statistics? So I couldn't be told you're rating this loss function. So you have another
Yeah.
loss, then how would you change that?
Yeah, so that here. So let's jump to some slides. Scroll down if this will. There we go. Okay, so before I had two types of loss, right? I said I'm just going to. So first of all, we're going to minimize over our betas. This 1 over n times the sum, the yi is equal to I, such that yi is equal to 1 of the loss according to that. So we had this sort of loss of y is equal to 1, and then we have our xi, and our beta. Right? And then we also had the losses for yi was equal to 0. This is our loss, loss 0 xi beta. Okay. Now, now the idea is that we would like this to be equal to, we would like to replace this. Well, we want to make sure that we have different weights for the different types of losses. So we're going to minimize over beta now, 1 over n. We're going to say that these losses, I such that yi is equal to 1, these losses are, let's say the, it doesn't really matter. We really just have to think about multiplying one of these losses by a number, right? Because we could scale it and then turn it into any proportion. So let's just say we're going to say multiply the losses when it's 1 by a larger number than 1. Right? This is applicable to the recommendation system. So we have our 0, 1 loss. We have 1 xi beta, and we're multiplying this by an alpha. So this is our new loss that's weighted. And then let's just keep the other ones the same, right? The yi is equal to 0, the same. So this is loss 0 xi beta. Okay. So so the particular choice of alpha that we used was just the proportion of ones in the data set, of true ones in the data set. So we made alpha, this is equal to the sum over I, such that yi is equal to 1 over over n, the total number of ones in the data set. So that's sort of the default choice. But if your application actually had a better way of weighting, right, based on costs or domain-specific ideas, then you would choose that better way of weighting. But one thing that I've tried to do is I've tried to motivate this idea of weighting losses through probabilistic models, right? Because a lot of times, like with logistic regression, when we introduce it, we say, well, let's suppose that the probability of being a 1 has this logit, you know, it has the logit of the probability is linear. Right? That's the logistic regression statistical assumption. Right? It's very difficult to motivate through an analogous generative model this class weighting, the weighting classes. There's some work on that by another faculty, another assistant professor in our department, Chodri, but it's very difficult to get to a point where this is actually motivated statistically. It's much more natural to think about these losses as surrogate losses if you want to motivate class weighting. So that's sort of the utility, I think, of entertaining different narratives for the motivation of our algorithms. So very little was, there was very little probability that motivated this, right? We were just thinking more practically about why should we care about, how should we care about different types of loss, different types of error, and then how should we turn this into something that we can actually solve, right? Actually compute. So anyway, I would encourage you to, in your practice, to entertain different ways of thinking about a problem simultaneously, because different ways, different things can lead you to different conclusions. Okay, more questions?
Okay, well, thanks so much for coming today. And Dave will be back next Friday, right here, same time, for part 2.
Yeah. We'll talk mostly about how to make it nonlinear, but also about overfitting. So,